Hello everyone, welcome back. Double Time here. Today we're going to be learning about powder rheology. So to get you all started, what is powder rheology? Well, in the real world, when you have multiple powders, they're very complicated and unpredictable in their behavior. So, powder rheology hopes to study how these powders behave as bulk assemblies so that we can understand how they will work. And in order to do this, we can measure things such as dynamic flow, bulk, and shear properties. So we're going to talk about what those mean in a little bit. So moving forward, what is a powder? Well, a powder is going to be the bulk assembly of solids, liquids, and vapors. And particularly in powders, solids are going to be these things called particles. So this is going to be an SEM image of talc powder, which is actually baby powder. And if we look at the top left, we can see that our scaling is at 20 micrometers. So these are going to be relatively small particles. And if we look at the screen, we can see that we have these different particles of larger and smaller sizes, different textures, different shapes, and these are all going to be different particle properties. And there's going to be a load of particle properties ranging all the way from hardness to elasticity to plasticity, and these are all going to contribute to something called powder behavior. Well, what is powder behavior? Well, this is going to be the accumulation of these powder attributes, going from all the way to flow to compressibility, all the way down to density, and we're going to talk about what those mean in just a little bit. And something that we can look at are these external variables, which can actually affect how powder behavior occurs. And these can be things like aeration, consolidation, and surface material. And so we're going to explore what those mean. So now that we know powder behavior and what it is, why is it important? Well, there's several industries that implement powders, ranging from pharmaceutical for things like your inhalers to your tablet creations, to things like food processing where you can be having flour delivered to you or baking powder to create everything that you're cooking. So, whenever these industries use powders, they actually need to be able to make sure that when they are manufacturing them, everything is going accordingly and as predicted. So things that they're going to be using powders for are these different applications we have here. So they can use things like hoppers and feeders or conveyors and mixing when they're creating it. And then when they're transporting and storing powders, they also need to make sure they behave in those aspects as well. And those are all going to be dependent on how powders behave. So, since we now know that powder behavior relates to the industry and why it's important, how do we measure it? Well, we're going to be focusing on three different types of powder behavior measuring, which are going to be dynamic flow, bulk, and shear testing. So to start us off, we're going to be going with dynamic flow. So we're going to start off with basic flowability. So if we look here, we can see this metal rod that with these different blades is going down into a powder sample that we have, and this is going to have a constant force that's applied along with a constant torque, and it's going to be able to measure the normal force along with the resistive torque along with the different height level that it's at. And these are all actually going to apply to calculating our flow if you see the top right hand equation. And essentially this is going to be our resistance to movement within a powder. So that's what flow energy is going to be. So when we're using our powder rheometer, something we want to do to our samples to ensure that we can have reproducibility of our testing is something called conditioning. So that's actually what this video is showing right here. This is showing a conditioning of a sample where the blade is going to be going through the sample, and it's going to make sure that has a low stress and steady state once it's completed. So it's going to go spiraling all the way down through the powder and then back up again, and it's going to make sure that every part of it is very aerated and to a certain degree, and that way it's more spaced out in the different particles within the powder. So continuing forward, we're going to look at aeration. So this is essentially going to be the same as what we just looked at, except we're going to be actually pumping air at a constant velocity through the bottom of our sample. So something that's important with aeration is that it's a very great measure to see if a powder is non-cohesive in its particles or it has cohesive particles. So a powder with non-cohesive particles, they're going to be able to separate more when the air flows through it, if you look at the picture above. And that means that the powder is going to have a lower flow or a lower resistance to movement within the powder because it's able to have the particles less interacting with each other. Whereas a cohesive powder is it going to have different particles clumped together because of the cohesive energy that's between them, and it's going to make it so that the air is only able to go through certain paths and not as fluid as we would want it to. So that's going to actually make the powder have a higher resistance energy or a higher flow. So if we look at the graph here, this is going to be showing that as we increase in our air velocity, we're actually going to decrease in our total energy or also known as our flow, or also known as our resistance to movement. And that's because we're going to have a larger separation of these different particles. Now, looking specifically at this graph, we can see that powder C had a drastic change in air velocity increase, but whereas powder A actually had a very consistent total energy throughout its process, and that means that this powder was already likely very not reactive to changes in air velocity. So that's just something to consider when you're trying to choose a powder. So moving onwards, we're going to look at and focus on consolidation. So essentially what we're going to be doing with this is if we have a powder sample, we can quote unquote tap it. And basically this means we're going to be vibrating the sample so that we can have the different particles become more dense with one another so they can take up the different places that air was previously before, so that way we can get this very, very consolidated sample. And if we see the little video here, when we have a consolidated sample, it has a very high resistance to flow, or a high flow energy, and it is going to do something called caking. So if we see here, we can have these little particle buildups, and those are going to be caking because the particles are going to want to clump together, and they're not going to move as much. Alright, continuing onwards with that, we have our graph here, and this is essentially going to say that as we increase in our tapping, our flow energy is also going to increase, so we're going to have a higher increase in our resistance to movement within the powder because our sample is so dense and it has an increase in mechanical and interlocking within the particles, and they're interacting with each other more, and that's just going to make it more resistive to movement. Alright, now we're going to look at bulk properties. So we can look at first at compressibility. So if we take a vented piston on our sample, we're able to compress it down with different stresses at different levels, and we can see that our compressibility percentage at these different stress levels, and that's going to be able to tell us what's going on with our sample. So if we look at the x and y axis here, on the x-axis for graph we have our normal stress, and then on the y-axis we have a compressibility percentage, and if we look at that, we can see as we increase in our stress, the percent that's compressed is going to also increase. And this is going to be different for different samples and how they react to different stresses. And also, something to note is if we have cohesive or non-cohesive particles, these are also going to react differently as well. So when we have cohesive particles, they're going to predominantly when they are put into a sample state, they're going to be more spread out and less dense because they are cohesive and they're going to be more clumped together in different positions. And then that's going to allow us to have a larger compressibility percentage based off the initial volume. Whereas if we have a very non-cohesive powder, those are going to be generally more dense in its form because these different particles are going to be able to find those different areas where there's space to be able to go to because they're not going to be clumped together like a cohesive powder. Alright, now we're going to look at permeability. So this is going to be is essentially the same as we were looking at before with our vented piston, except now we're going to be flowing in a constant air velocity through the bottom of the sample. And essentially what this is we're looking at is we're trying to measure our air pressure drop across the powder bed. And if we have a sample that is more permeable, more air can pass through it, so there's going to be a lower percentage drop. And if the sample is less permeable, then less air is going to be able to get through it because of these dense particles interacting with the air that's coming through. We're going to get a percentage drop that is actually higher because the less permeable substance has less air going through it. So if we look at our x and y axis here, we have our applied normal stress, and then on the y axis we have our pressure drop across the powder bed. And we can see as we increase our stress onto the sample, our pressure drop is going to increase for most of the samples. Now if we look at A, we can see that its pressure drop is not as high, and that's probably because this is a very, very permeable powder, and it's able to allow air to pass through it even when at high stresses. Alright, now we're going to look at shear testing. So to start us off, we are going to typically have this testing head, which if we look at the top of there, we can see that we have a constant stress that we're going to apply onto our sample at different intervals of stress. and we're going to have a torque that's also applied on the sample. And what this is going to do is we have these different blades that are coming from the head that go into the sample, and it's essentially going to create a disk of powder that is going to move onto the other sample part of the powder. And we're going to try and see what the initial torque to overcome friction between this powder and itself is, and we're going to measure that at different stress levels. And we're also going to do the same for wall friction, except instead of using powder against powder, we're going to use a material against powder, and we're going to see what the required friction to required torque is to overcome friction for that sample. And that's going to be important for things like developing hoppers. We want to make sure our powders don't stick to the materials that we're trying to use to transport them if we want to make sure that they have good movement. So if we look at our graph here, we can see on our x-axis we have our normal stress, and on our y-axis we can see our shear stress. And this is basically going to show that as we increase in our stress, we're also going to increase in the amount of torque required to overcome friction. And if you see all these different angles and wall yield locus on this graph, essentially what this is saying is our higher slope, the higher the slope is on the graph, the more shear stress is going to be required to overcome friction predominantly for the sample. So anyways, that's going to be basically it. What you guys learned was a lot. We went from all the way from powder rheology to powders in the industry to understanding powder behavior with dynamic bulk and shear testing. So I hope you all learned a lot, and I am very thankful that you all watched this video. So thank you very much. Hope you all have a great day.